So good afternoon, everybody. The first speaker of this room is Raghu Mahajan from International Center of Theoretical Science, Bengaluru, and he will talk non-perturbative minimal superstring matrix integral duality.
Okay. Thank you, Kenji, and thank you to the organizers for the opportunity to speak. So before I start, I would just like to say that please feel free to ask questions during the talk. I want this to be informal since we have a small, cozy group. And just in order to get to know the audience, how many of you are PhD students? Hi, there is that. Okay. Postdocs? Okay. And faculty? Okay. Good to know. So just please stop me anytime and ask questions. I want this to be interactive and so on. Okay. Okay, so this talk is about string theory and non-perturbative effects in string theory. It's well known that many interesting observables like scattering amplitudes, the basic observables of flat space string theory, contain contributions of order e to the minus 1 over g string, and these arise from so-called d-instantons. So gs is a small number. Think of it as 1 over 137 or some very small number. So in the exponential, you have a large negative number. So it's a very, very small effect. Okay, and these come from the so-called d-instantons. These are much smaller than what you would see in perturbation theory, which are just powers of G string. This is e to the minus a very small number. Okay, so a very concrete example is a particular term in the 4 graviton scattering amplitude in 10D type 2B string theory. So we just have 10-dimensional Minkowski space, and you send in 2 gravitons, and 2 gravitons come out. So here there are some perturbation theory. You can see there are powers of G string multiplying some special numbers and another power of G string. But then there is a term which is, you see this exponential of minus 1 over G string. And it's multiplied by a number, 8 pi, and a power of G string. So the interest of this talk is to calculate these numbers very precisely, this 8 pi and this particular power of G string that appears here. So that is the goal. How do we derive these numbers? Now, this formula was written down by Green and Gutperl, just invoking S duality of type 2B theory. So these numbers have not been derived, or they were not derived from worldsheet string theory until a few years ago. Okay, so is this clear? What's the kind of goal of the talk is to compute these numbers that multiply these exponentially small corrections to various observables in string theory. Okay, so it's well known from the work of Polchinski that such terms can arise from open string worldsheets with Dirichlet boundary conditions imposed on all space-time coordinates. So not just space, but also time, you put these Dirichlet boundary conditions. And the point is that worldsheet perturbation theory with these boundary conditions is often ill-defined. The resulting answers contain undetermined constants that need to be fixed using other assumptions, like we just discussed, S duality in type 2B string theory. And here are some works by Green and Gutperl in type 2B. This set of authors in the early 2000s studied this in the context of minimal string theory. And then more recently, non-perturbative scattering amplitudes were studied in the C equals 1 string theory by the group at Harvard, Shi Yin and his students. Okay, so the worldsheet perturbation theory seems ill-defined, so what do we do? So in this talk, I will explain the basic string field theory idea that allows us to overcome this fundamental obstacle in dealing with these perturbation theory around the instantons. And this idea is due to Ashok Sen. And these ideas were first developed recently in the context of two-dimensional string theory. And now these have been generalized to tackle various effects in 10D superstring theory and also its compactifications. So these are no longer toy models, these are actual serious compactifications, leading to highly non-trivial checks of superstring dualities. And here are also some more authors from the Boston area and France and around the world who have contributed to this work in recent years. Okay, so our setting will not be 10D string theory because it's a little bit complicated. our setting will be the so-called minimal string or the minimal superstring. And we will show that this string field theory procedure produces instanton contributions that match perfectly on the nose with these dual matrix integrals. So these minimal strings are dual to certain non-gravitational theories, and we can check the answer using the dual description. Okay, so here is a set of 6 papers I have written so far on this subject, and at least a couple more are on the way. And my collaborators, that's a student at Stanford, Dan Enicheku, he's really strong calculator, and he'll be on the market this fall, so please hire him if you have postdoc positions. Okay, so why should you study this minimal string theory? Just in terms of motivation, you say, I am interested in actual real world physics, and this minimal string, what is it? Why am I interested? It's a toy model of string theory, but simplifying toy models as much as possible is valuable. Many times it's very valuable, and one example of this recently is in this particular context of de-instanton perturbation theory, there was an apparent mismatch that was found between the 2D string theory and the matrix quantum mechanics in a particular observable, which is this closed string annulus 1-point function. It's a particular quantity. People saw that the results are not matching on the two sides of the duality. So what we did, for example, in this paper, is you go to an even simpler model, this minimal string, and you can resolve it there. And once you've resolved it there, you can go back to the parent problem and see that things work there as well after you've identified the subtlety in the calculation. So I want to emphasize the usefulness of toy models. Minimal strings is one, topological strings is another. Okay, so that's why we study this. And the lessons generalized, that's the point. Okay, so here's an introduction to this minimal string and the duality to the matrix integral. Just again, in terms of motivation, since we also have PhD students here, 3 plus 1 dimensional gauge theories are hard, even in the large n limit. The fields there are matrices, so you have a space-time index mu. There are space-time coordinates t and x, and there are color indices I and j. Okay, so this is a gauge potential in a SUN gauge theory. Yet, if we are only interested in the planar diagram expansion, only the ij color indices are responsible for the topological expansion. The mu, t, and x are not really important. So this motivates the study of 0 plus 0 dimensional gauge theories where there's no space-time at all, and all you have is a matrix-valued field with only color indices ij. Okay, so the path integral in this setting is just an ordinary integral over one or more matrices, and it strips down a 't large n idea to its bare bones, to just the color indices. And this was studied in a famous paper by Brazan, Itzix, and Parisi and Zubair a long time ago. Okay, so is this clear what we are studying? We are studying sort of integrals over matrices in this thing. Okay, so research along these ideas in the 80s and 90s led to a precise duality between these matrix integrals and non-critical string theory. And it is the earliest example of a duality between a gravitational and a non-gravitational system. The gravitational system is the string theory, and this non-gravitational system is this matrix integral. And this subject was sort of discovered in two kind of periods. One is the late 80s, early 90s periods, and here are some authors, there are many more. And then in the early 2000s, after a Liouville theory was solved using the bootstrap, especially the groups at Princeton really worked a lot on this duality in the early 2000s. Okay, so now I will introduce the two sides of this duality in slightly more detail, and then I will describe what particular observable we are computing in this theory. So the observable is very simple, it's just the partition function or the value of the integral itself. So here the integral is denoted by z. Sorry. Z depends on a few numbers. N is the size of the matrix. So M is an n by n Hermitian matrix. And this T is the 't coupling. It sits in front of the action in the denominator. And this V of M is a polynomial. So for example, you could take it to be some coefficient x squared, some coefficient x to the fourth. So this number depends on N, T, G2, and G4. In going to the second line, we have used the standard conversion from the integral over the matrix entries to the eigenvalues because it has a UN invariance. So this delta of x squared is a Jacobian factor that comes when you do this change of variables. And in the end, you just have an integral over n eigenvalues of this matrix M. Xi's are the eigenvalues. And the particular case we want to study is G2 to be positive and G4, let's say, is negative. And this is done because I'll explain on the next slide why this is important. Don't worry about the convergence because if G4 is negative and there's a minus sign here, you just need to appropriately choose the contour of these x's so that it's convergent at the ends of the two contours. So that is no problem. Instead of integrating x on the real line, you just integrate it on some curve in the complex plane. But the perturbation theory anyway doesn't know about the full definition of the integral. Okay, are there any questions about this? Especially from the students or people who might not have seen this before? Okay, all right, so let's move on. So what we have to do to get to the string theory description is we have to take the so-called double scaling limit. So what happens in that limit is you have these parameters t, n, g2, and g4. You have to tune them to certain specific values. So the t, you have to take it close to g2 square over minus 12 g4, and the deviation from that is this epsilon square. And the n also you take to infinity, but epsilon is going to 0, so this product kappa you hold fixed. Okay, that's just the definition. What happens in this limit is that Feynman diagrams with a larger and larger number of vertices give the dominant contribution to this integral. And because these big diagrams are giving the dominant contribution, you can take a continuum limit. You can take a continuum limit and the 2D surfaces, the Feynman diagrams, become smooth in this limit. So that's why the connection to continuum string theory is only there in this limit. And only recently, the work of Rajesh has discovered dualities of non-double scaled integrals. Okay, so now this kappa instead of G string becomes the genus counting parameter. And this is a picture taken from some mathematicians' work who have also studied Liouville theory and random surfaces a lot in the recent years. So it will look something crazy like this. Like this could be a Feynman diagram of, let's say, this phi-4 theory where each vertex has 4 phi's coming out of it. Okay, so now I have described to you the matrix integral is just some matrix, there's some potential and you're doing an integral. What is the string theory? The string theory is typically described using its worldsheet theory. And the worldsheet theory consists of 3 sectors. They're completely free from each other and they're coupled only by the Virasoro constraints. So there's a minimal model, there's a 2, p minimal model, which is generically a non-unitary 2D CFT. And this can be thought of as a matter sector having central charge less than 1. There is the Liouville CFT, which is a remnant of the conformal factor of the worldsheet metric. It no longer decouples because the central charge of the matter is not 26. So this has a compensating central charge 1 plus something, which is bigger than 25. And the sum of them is 26 and is cancelled by the BC ghost CFT. So this is the second side of the duality, the string theory, which has these component CFTs on the worldsheet. Okay, so what are we computing? We are just computing Z. And in the matrix integral, in this large N or the double scale limit, it's known that it can be written as the exponential of 't Hooft's large N expansion. So there's a term proportional to kappa squared, which comes from spherical or planar diagrams. The next term comes from torus, the next one from genus 2, and so on. And they have kappa should be thought of as a large number. So it's organized in inverse series of kappa squared. So this term is smaller, the next term is even smaller, and so on. So this is just the genus expansion. And on the string theory, you have the sphere worldsheet, the torus worldsheet, the genus 2 worldsheet, etc. So we sum over all closed Riemann surfaces with no vertex operators. And at each genus, we still need to do a moduli space integral. The genus 2 surface, for example, would have a 6-dimensional moduli space. Okay, so this is the normal perturbative expansion. Now we go to the instanton story. So here I wrote this 0 because this represents the leading kind of saddle point and the perturbation expansion around that. Generically, there might be a d-instanton configuration, and the contribution of that to the whole partition function is denoted here by Z1. 1 refers to the number of instantons. So here there is 0 instantons, and now we have a small term which has 1 instantons. And the ratio of these two can be written again as an exponential of a different power series, but now in powers of kappa inverse instead of kappa to the minus 2. So the leading term in blue here is something proportional to kappa, and it will be proportional to the disk diagram in the string theory. And the boundary of the disk will have these all Dirichlet boundary conditions. And these brown terms are the next terms. There's a constant and actually a logarithm in kappa, which come from the annulus. So because you have a logarithm and this exponential, that will produce the power of kappa up front in this thing. So you remember in this Green-Gutfeld formula, there was a power of G string to the 3 halves. So that comes from these logarithmic terms, and the number comes from this D1. Okay, so those are the leading terms in the string theory, a disk and the annulus. The annulus, yes. The annulus is the one loop. In the matrix language, yes. So kappa is the, sorry. So this first term is the instant on action, and the brown is the one loop determinant around, exactly. Actually, even on the string theory side, the annulus is kind of like a one loop of the open string. So yeah. Well, the instant on action is usually 1 over G string, and that's kappa. So, I mean, it really depends on what we call the tension after a certain point. So it's, yeah, I guess one could call it. But there's also, for example, powers of kappa inverse and kappa to the minus 2 and the whole series. So I think it's better to just organize it using the topology of the string theory. But maybe you have something else in mind about changing that. Okay. But there is some correction to the action coming at one loop. Or no? Okay. Yeah, I would just think of this first term as the action, and then this thing really as the one loop. And then there are 2 loop and so on. Yeah. Thanks for the question. Yeah. Okay, so this is what we are after, this brown term really. Okay, so we write this as exponential of disk plus annulus. This disk part gives something minus 1 over G string, and the exponential of the annulus we call the normalization prefactor. That's just the name. And the goal of this talk is to compute these precise numbers with the precise order 1 constant. So what happens in this minimal string theory that I showed you is that this n, which is the exponential of this annulus, has a power of G string, which is 1/2. It has an imaginary part I, and then there is some number which just depends on P. Okay, and it's important to note that in this equation, the normalization of GS is chosen so that the action or the tension of the instanton just equals GS inverse. So that's the definition of G string. Otherwise, the precise number is ill-defined because of this power. So this is the result. Sorry? P was the P in the minimal model. So the minimal model CFT has 2 integers, P and P prime, and we are, in this case, we have taken the 2 comma P minimal model on the worldsheet. So in fact, the P goes to infinity limit of this is JT gravity. So the original motivation of this was from the work of Saad, Schenker, and Stanford, who were discussing these kind of effects in their paper called doubly non-perturbative effects. And this order overall constant was kind of not computed in that paper. But it's this same family of theories, and you see the P will cancel in the P goes to infinity limit between these factors. Okay. Yeah, we have done that in a follow-up paper, yeah. So even if you have a P comma P prime minimal model, there it's more complicated because it's dual to a 2 matrix integral, but it's possible to do that, and it also matches precisely. I just haven't presented the formula here. Okay, so the goal is to reproduce this number from the string theory side. From the matrix side, I will show you how to do it, but it was more or less known even in the early 90s. Okay, any more questions about this? Okay, all right. So here's the string theory computation. So first, just a comment, the disk and the annulus are worldsheets with a boundary. So we need to specify conformal boundary conditions for all component CFTs in the worldsheet theory. Most importantly, it's for the Liouville CFT. The relevant boundary conditions were discovered in the early 2000s, and they are the so-called discrete family of ZZ boundary conditions. ZZ stands for Zamolodchikov and Zamolodchikov. So there are a discrete family, but we'll focus on the so-called 1,1 ZZ brane for simplicity. So we'll just focus on this particular case and explain the answer. Okay, so this annulus that we want to compute has two boundaries, and we put both of the boundaries on this ZZ brane and ask what is the annulus amplitude. So in the open string channel, it looks like a loop. At a given length to circumference, width to circumference ratio of the cylinder, that's T, we have a trace in the open string Hilbert space of e to the minus 2 pi t L naught. That's like a Boltzmann factor. And then an insertion of the zero modes of the BC ghost, because you just need to have them, otherwise the answer will be zero. Okay, and this dt over 2t is the well-known measure for integrating over the moduli space of the annulus. So the point is that the answers for this trace are known using the bootstrap. So we have the minimal model, we have the Liouville CFT, and the BC ghost. So separately, you know the annulus partition function for all of them. You multiply everything, and you find that this trace, which goes in the integrand here, has this representation. So this is some e to the 2 pi t minus 1. This comes from the Liouville sector. There's an infinite sum. This comes from the minimal model with the plus and minus signs accounted for this nested sequence of null vectors in the Verma module. And the denominator eta functions cancel in this low dimensional setting. There's one eta from Liouville, one eta from the minimal model, and the ghost given eta squared upstairs. So it's just this. Okay, so what's the problem? The problem is we need to integrate this with respect to t. And when you take this is just copied from the previous slide, and you expand it at large t, you find these two terms, e to the 2 pi t and a minus 2. And the rest are exponentially suppressed at large t. So when you try to do this integral, there's a divergence coming from infinity. So this is ill-defined. Yeah. So actually, I will comment on it later, but just quickly, there are, even in the matrix side, there are a series of instantons because the effective potential has multiple minima and maxima. And the discrete family of ZZ instantons is in a one-to-one correspondence with those maxima. So we actually computed it for all of them, and they all match. But that's some simple generalization. Sorry? Yeah, you could match them just by matching the tensions. So the ratio of the tensions and the ratio of the heights of the effective potential agree precisely. But as far as this puzzle is concerned, they will all have the same problem and the same resolution. Right. So in fact, if you know, the 1,1 is the one that's closest to the cut in some sense. Yeah, so that's the first one in some sense. Okay, so this A is ill-defined, and that's the source of all these problems that I was saying in the beginning, that people cannot compute these normalization constants. They seem to be ill-defined, and what do we do with this? Okay, so the point is we need to get to the bottom of what are these being counted. What is being counted here? Because we are doing some trace in the Hilbert space, so we need to know what these states are. Okay, but first, we first have to realize one fact, which is that exponential of the annulus is in fact a better quantity to consider. Anyway, it was the exponential of the annulus which was appearing. The A was not even appearing. It was e to the A. And it's possible to make e to the A actually well-defined, not A itself. Okay, so we write this trace in the open string Hilbert space as a sum over Grassmann even degrees of freedom and Grassmann odd fields. There are Grassmann odd fields because of the ghosts. So you have the BC ghosts, so certain things have minus signs, and this also contributes there. So anyway, so there are some minus signs there. And when you do this integral, there's a simple formula. When you have a difference of exponentials and a dt over 2t, the answer is a logarithm. It's a logarithm of the fermionic weights on top and the bosonic weights on the bottom. It's infinite product divided by infinite product. So when you take the exponential, this logarithm goes away, and you're just left with the ratio of these products. This prime just means that the fermionic weights always come in pairs. So you can remove the power 1/2 from the numerator and only do a product over half of them. And then you realize that this product is nothing but a Gaussian path integral over a bunch of bosonic fields phi b with the kinetic term hb is just a number, and a bunch of fermions, Majorana pairs, with the weights hf. So what you have done is basically rewritten the e to the a as a kind of a path integral. Okay. So the annulus diagram is, as I was saying before, is a sum of states, single string states in the Siegel gauge. When we exponentiate this annulus, when we exponentiate single particle quantities, we get multi-particle quantities, right? So that's like multi-partling the single string trace. So what we get is a Gaussian approximation to the path integral of the D-brane world volume field theory, right? We have a D-brane in the game, there's some open strings connecting them, and there should be a field theory that describes this D-brane. So in the well-known case of D3 branes, this would just be the n equals 4 super Yang-Mills, right? So this is some D instanton, it's a D-1 brane, so it's a 0 plus 0 dimensional theory. And there's one field for each single string state, just like in second quantization. There's nothing more fancy here. Okay, so this is the meaning of the formula. So when you wrote the exponential as an integral over these fields, phi b and pf and qf, this is really the path integral of the D instanton world volume theory, or the path integral of the open string field theory. You can use whatever words you want, but that's what this number is. Okay, so now with this understanding, let's go back to those two terms that were problematic. So this e to the 2 pi t, comparing it to e to the minus, remember, it was e to the minus 2 pi t times hb, right? So hb equals -1 will give the e to the 2 pi t term. So when L0 is -1, those states are called tachyons. So this D brane has an open string tachyon on it. And the vertex operator for the tachyon is just the C ghost acting on the vacuum. And the coefficient field is called T. So the world volume path integral contains the following integral over T. Because its H is negative, it's unsuppressed Gaussian. It's e to the 1/2 T squared. Okay. So now, of course, if you integrate this over the real T, it's ill-defined. So that does not make sense. So what you say is that the path integral is such that it goes over the imaginary values of T. And then it's okay. And that is what was producing the factor of I in this normalization constant. Okay, so the I comes from the tachyon. Okay, so now there is a choice of the steepest descent contour and some signs. Let's not worry about that because there actually happens to be a one-to-one correspondence between the choices in the string theory and the choices in the matrix. So if you just integrate this from minus I infinity to I infinity, so like vertical in the complex plane, you just get an I. So that's the I that was there in the final answer anyway. Okay, so now we want to go to the next one. There was also a problem with the -2, right? There was e to the 2 pi t -2. So because of this minus sign, you know that they are fermions. And there's no power of t here, so you know they are zero modes. So there are two fermion zero modes. And this is really the heart of the problem. So if you want to take something away from this, it's the next few slides, because that's really at the heart of the matter. Okay, so we are dealing with these D-1 branes, but first let's think of the dp brane for p bigger than or equal to 0. Okay, so let's think of a D3 brane for concreteness. It's a gauge theory and it has a gauge field, right, A mu. So it needs some Faddeev pop of capital B, capital C ghosts, I'm calling them here, for the perturbation theory to be well defined. Otherwise, the kinetic term is not invertible. So the fields in the world volume gauge theory are the following. So if you look at the open string vertex operators, there's an e to the I momentum time x, and this momentum is a vector that lives in p+1 dimensional space. This is the standard vertex operator for a gauge field, and this is the coefficient. But there also happens to be at the same L0 eigenvalue, this C0, which also has weight 0 times this psi k. So there's actually a pair of fields, and typically this one is not written down in books. So let's look at these two. And what happens under gauge transformation? So we know from in the string field theory language, gauge transformations are implemented by BRST exact terms. So you can do a BRST transformation on just this e to the ikx. This theta k is just some number, is some complex number, is the gauge parameter. And when you do this gauge transformation with theta k, you get the following. A mu transforms like a gauge field, like you know, but the psi also transforms. It goes to plus k squared times theta. So both of them transform. And what typically you do is you use this gauge freedom to set psi k to 0. So you set some field to 0, and but you have to introduce, the ghost fields, which have the following vertex operators. So you start with an ill-defined path integral over a mu and psi, but then you go to a different description where the psi is gone, and you have this capital B and capital C Faddeev Popov ghosts. Okay. Is this clear for the general gauge theory? Okay. So why the d instantons are special? So this is just copied from the previous slide. So what happens is that on a d instanton, there is no momentum. You don't have this k at all. So you have a capital C field and a capital B field, which are just numbers, right, that we know. And these are the ones that are giving you this -2. So somehow, when you're doing this worldsheet computation using the bootstrap, it already has these Faddeev Popov ghosts in it at ghost number 0 and ghost number 2, and that's what is giving you this -2. Okay, even for a d instanton. So there was one tachyon, and you have 2 of these Faddeev Popov ghosts. So this must be something weird because we have these Faddeev Popov ghosts, and these were the ones that are causing the problem. So just to re-emphasize, in the path integral, you have this Majorana pair, dB/dc, and it has this weight equal to 0. It's e to the 0 times bc, so that gives you 0. Okay, so that's the source of this ill-definedness of this normalization constant. Okay, so what should we change? But the point is that on a d instanton, right, there is no gauge field. Because the gauge field requires a mu index, and you don't have a mu. It's a 0 plus 0 dimensional field theory. There is no alpha -1 at all on the thing. And this gauge field that got set to 0 had this non-trivial transformation law, was multiplied by k squared times theta k. But on a d instanton, you don't have a k, so the psi is actually gauge invariant. If something is gauge invariant and you're integrating over it in the path integral, there's no way to just set it to 0. Because the thing you can set to 0 is something that transforms under the gauge symmetry. So that's the problem. The problem is that the worldsheet is kind of secretly working in the wrong gauge from the point of view of the world volume path integral. Okay, so psi is a gauge invariant state, and there's no way to set it to 0. So this Faddeev Popov procedure is illegal for the case of a d instanton that we use to set psi to 0. So the remedy is very simple, and this is the insight of Ashok Sen, is you just throw out these BC fields. And from the string field theory perspective, in the BV formalism, is just picking a different set of variables to integrate over. So you put back this psi field, you don't throw it out, but then you divide by the volume of the gauge group. So what is the gauge group here, right? Typically, imagine that you have a D0 brane, so you'll have a world line, right? And imagine that it's discretized. So this is D0 brane, and this is time. At each instant of time, you'll have a U1 group. That's what a gauge symmetry is. But on a D instanton, the world volume is just a point. There's no time, no nothing. So the gauge symmetry is just U1, that's it. There's no U1 for each point on the world volume. So this gauge group volume is just some finite number. It's just some 2 pi with some scaling. And that you work out correctly, and it has this power of the open string coupling constant in it. So this thing that was giving you 0 before, this was not correct, and this is the correct thing to do. Because the Faddeev Popov procedure, you shouldn't have gone this way. You should have kept the string path integral in this form. taking this step was illegal. And this is not some mystery. You see, anytime a gauge fixing procedure is bad, it shows up as a zero mode of the ghost system. And this is reflected in the fact that the standard ghosts are massless. So their kinetic term has a momentum, is proportional to k. And that's reflective of the fact that gauge transformations don't change homogeneous modes of the gauge field. So on a compact manifold, the holonomies are gauge invariant, right? That's what it means. And that's why the ghosts are massless. Here, there is no momentum. So the constant mode kind of is the only thing you have. Okay. So the gauge group volume is finite, and you have this other field, and you get this number. And you can convert G naught to the tension of the D brane, because the open string coupling is related to the tension using this formula that was in a work of Ashok also from 20 years ago. Okay, so basically what we have done is we have replaced this exponential of the annulus with an integral over the tachyon, an integral over the psi field divided by the volume of the gauge group. But there are also these dot, dot, dots, right? So there wasn't just these two terms, but also like there was a whole bunch of additional e to the minus 2 pi t terms. So you also have to take those into account, and that's so you get something like this. And after you do this, it's basically very simple. You just get the whole result back. Just to emphasize, the I again came from the tachyon. This power of G string came from here. And this cotangent comes because the cotangent has an infinite product formula. And that's what you get from these other integrals. Okay. So that's the final resolution, and that's basically it. So I want to pause here for questions because the rest of the talk is just going to be some generalization and the matrix model and so on, but I want to make sure that's at least this procedure was clear, like what we are doing in this step. Yeah. Okay. Oh, so I will come to that. I have some slides on that, so that I will come to. Eva? Yeah. Well, in this case, the intuition is just coming from these higher DP branes, because you see the fields are the same. If you look at these vertex operators, right? These are the ones we had for a DP brane. It's just e to the ikx and this C1, C minus 1 e to the ikx. And these we know are the Fadi Popov-Gauss on a D3 brane, for example. But just when you go to the D instanton, this k is not there anymore. So another way of saying it is, it would have been a gauge symmetry had it been a D0 brane or higher. On a D minus 1 brane, this world volume is just a point, so you can call it a global symmetry if you want. Right? The point of a gauge symmetry is that you can do it independently at each point of space-time. And the D instanton world volume is zero dimensional. So there's just a point on the world volume. So in fact, the distinction is not important. So, but yeah, it's a finite volume. Yeah, so you divide by it. So in some sense, you are gauging it, but you are dividing a number by a finite number. So it's kind of hard for me to say whether it's gauged or not, because it's just the whole group. That is crucial. Yeah. So in that sense, you're dividing by that. Yeah, volume. Uh-huh. I see. Yeah, I guess that's a good point. Like typically all the states you have are invariant under this U1. So you don't have any states that are in, yeah. Right. So I guess it's, yeah, one could call it a gauge symmetry in that sense. Right. Yeah, well, I guess this gets into this question of even this recent papers by Juan and Alexei, whether even in the D0 brane quantum mechanics, you can consider the gauged model or the ungauged model, and there might be holography for the ungauged model as well. It's not clear in that case. But in this simpler case, I think it's fair to say that it's gauged, like the most standard case is gauged. Okay, thanks for the question. Any other questions? Okay. Okay, so here's a summary of the string calculation. Somehow the worldsheet theory is producing an answer for the annulus that is in a bad gauge from the point of view of the D-brane field theory. And the string field theory helps us identify the culprit modes. And the new world volume path integral, which has this new field, produces a finite unambiguous answer. And a comment is that once you have this field in the path integral, it will also propagate on internal lines in Feynman diagrams. And in string perturbation theory, internal lines in Feynman diagrams appear in corners of moduli space. So when your Riemann surface degenerates, and you will need to take into account the exchanges of this new field in order to get finite amplitudes for other quantities. And these contributions will be completely missed by standard worldsheet perturbation theory. So somehow you need to chop up the moduli space by hand, and near these corners, you need to by hand stick in this extra field with this Feynman diagram on the internal lines, this new field. So in some sense, what string field theory is just a mechanism for doing string perturbation theory correctly. So it's too quick to say when we say in Polchinski, we say that, oh, the moduli space integral is all there is. What you're hiding from there is there are a lot of infrared divergences that you need to deal with. And to really deal with those infrared divergences, string field theory is the proper mechanism. So people get kind of scared when they hear the word string field theory. It's nothing fancy, but just a way of doing perturbation theory correctly. At least in this context, that's what it is. But what I'm saying is that's the only job it's doing right now for us is to set up the perturbation theory correctly, at least for the closed string field theory. Because at these boundaries of this moduli space, there are all these divergences and you don't know how to make sense of them. And this was an example. Okay, all right. All right, so now for the matrix integral computation, since it was, sorry, Kristen has a question. Well, so that's actually a choice in string field theory, like how you chop up the moduli space. You can pick however you want it. The point is all those ambiguities go away. The point is the singularity is infinitely far away in some sense, according to some metric. You cut it off at some point, but that cutoff is irrelevant. Yeah. Okay, so here's the brief summary of the matrix integral computation. It was already worked out in the 90s. The main point is that the effects come from these one eigenvalue instantons, which are extrema of the effective potential. So if you have a single eigenvalue in this n eigenvalues, it feels not just the bare external potential, but also a logarithmic term coming from this van der Maan determinant. Remember when we did this change of variables, there was a delta of x squared downstairs in the path integral. So that has some x minus y square type terms. And that you put in the exponent. So this row of y is the density of eigenvalues. And this logarithm is the van der Maan repulsion coming from that gas. So you might see this formula, for example, in 3D electrostatics, where you have a gas of charges. And instead of a log, you'll have a 1 over x minus y in the potential. Okay. So, but this thing does something non-trivial. These two terms are both important. And so a single probe eigenvalue can be at a stationary point of this effective potential. So here is an example. So if you take this 2,7 CFT, this effective potential has a particular form. So this is flat here. So that means that all the eigenvalues are here. Okay. and then a single probe eigenvalue fields this effective potential. So this point, and this point are just stationary points of the integral. Gentlemen, you have? Okay. So what you should imagine, there are two saddle points. The first saddle point is where all n eigenvalues are here. Nothing is outside, all n are here. That's what the closed string perturbation theory discusses. Then you have a second configuration where you could have, let's say, n minus 1 of them on this cut and 1 on top, or 1 here. Or you could have something like n minus 5 here, a 2 here, 1 here, and 2 here, something like that. So that's the generic configuration you can have. Okay. So what we need to do to get the one loop constant is here, it's trivial. You have this thing sitting on top here. You have an exact formula for this V effective, and you just need to do a Gaussian integral around that. So the V effective at the critical point is the on-shell action, is proportional to kappa. And this 1 over square root of kappa is painfully obvious in this form because the integral looks something like e to the minus n x square integral dx, okay, or kappa. So that's like 1 over square root of n, which is like g string to the 1/2. So this factor of g string that we had to work hard to get in string theory is like obvious in this matrix integral set. Okay, so that's all, and this number you can check. I will not produce the details, but the answer matches the string theory computation. So does that answer your question? Okay. So it's just some Gaussian integral about a maxima of a potential. Yes. Yeah. Well, in the end, we didn't have to work so hard, but you had to realize that in some ways of doing the calculation, the volume of this U1 group had that factor of G string in it. So remember, yeah, it's a little bit subtle, but it's related to how if you're doing a path integral and you delete some modes in that path integral, you get some powers of the coupling constant up front, like these logarithmic corrections to black hole entropy, for example. So it's related to that kind of subtleties, which is well understood. Yeah. 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 Yes. Well, the matrix model version of that would be, so you mean for annuli that have endpoints on different branes, right? So you had this effective potential, right? So imagine that you put one eigenvalue here and one, let's say one here, right? So now you'll have some integral that's like dx, dy, e to the minus n v effective roughly at x, minus n v effective at y. But there will be also a van der Waals repulsion between x and y. So this is x minus y squared. So that cross annulus is computing this term. So, yeah, thanks for the question. And you can put multi-instantons and you'll have the appropriate factors of the appropriate van der Waals going in. Okay. All right, so here's just a comment about contours. So the duality between matrix integrals and string theory, at least in this particular setting, happens to sort of hold around each saddle point. And here by saddle point, I mean the collection of these eigenvalues and so on. We need to specify a defining contour for the eigenvalues of the matrix integral, and that will pick out a particular linear combination of these Lefschetz thimbles. But the point is that the string theory also needs a corresponding defining contour in the open string tachyon plane. So somehow you seem to get more. It's not just a duality between kind of the whole path integral. It's somehow seems to know about each saddle point individually. And you can pick some contour on both sides that's sort of correspondingly, the same on two sides. That's just some intriguing thing that you realize when you work on these problems. Okay. All right, so here's a summary again. The worldsheet description is inadequate, and these insights from string field theory help us to obtain a finite, unambiguous answer for the normalization. Okay, so here are some generalizations. Two matrix integrals was already asked. An arbitrary multi-instanton configuration you can also do. Collier, Eberhardt, Muehlmann, and Rodriguez generalized it to their recent Virasoro minimal string. And we also studied this type 0b minimal superstring, which was discovered in the early 2000s by the Princeton group. And the interesting thing here is that there are two phases of the matrix integral. There's a gapped two-cut phase and there's an edgeless phase. They kind of correspond to the two phases of the Gross-Witten-Wadia model, if you know about that. And in each phase, there are instantons, there are corresponding string theory instantons. The only thing is that because now you have the superstring, there are the beta gamma ghosts. So the ghost structure is different, but there are still some these zero mode problematic gauge states that you need to throw away, put in some other state, and the story is the same. So just to give you an idea, here are what the two phases look like. In one phase, there are eigenvalues on these cuts, and there's a gap in the middle, and you can have instantons at these maximas. This is the plot of a real part of the effective potential. And in the other case, you look at the complex plane, the eigenvalues are everywhere, but these instanton locations are at a complex points in the eigenvalue plane. So you need to deal with complex instantons. And in fact, there is some extra subtlety that the things that actually contribute in this phase makes a connection to ghost instantons that are recently discussed by Marino, Schiappa, and Schwick. So I'm now in the phase of the talk where I'm not explaining much, but giving you some palette for the results that you can go and look up in these papers. So just to emphasize, in this type, in the minimal superstring, the interesting thing is there are two phases. Both of them have instantons that are qualitatively very different. And they both agree on the two sides of the duality. Okay, so here are two questions for the near future. I think this is really interesting. So consider this type 0a minimal string and in the gapped phase. It is known that it's dual to matrix integrals over complex matrices. And you're integrating over complex matrices, not Hermitian matrices, so the measure over eigenvalues is different. It has this lambda here and this thing. In the gap phase, there's an eigenvalue instanton exactly at lambda equal to 0, which sits at a fixed point of the Z2 symmetry that acts by lambda to minus lambda. So it's like a D-brane that's sitting at an enhanced symmetry point, and you know that there are extra effects that can happen. So what happens is that this quadratic action around this instanton has this additional lambda here. So it's d lambda, lambda, and a lambda square and an n. So now the power of n is different. Instead of having this 1 over square root of n, you have a 1 over n. And it's okay, so that's different. And this leads to a different power of G string. It should be G string to the power 1 as opposed to the earlier case, G string to the 1/2. And so this power of G string cannot just be explained by the volume of this U1 group and removing this unwanted pair of ghost fields. So what we believe should happen is that there are 18 zero modes, even in the simplest case, 10 of which are Grassmann odd and 8 are Grassmann even. And the resolution, we believe, lies in evaluating the following integral. So there are 18 of these zero modes, and there is a quartic coupling between them. These x's are the fields, and j, a, b, c, d's are the coupling constants. And you just need to evaluate this integral. And the interesting thing is that the quadratic term is 0, and the leading finite part of the integral is coming from an x to the 4th type term with no quadratic term. And a simple scaling argument actually predicts the correct power of G string, but we also want to get the number, and for that, the hard part is calculating these numbers, J, A, B, C, D, which are disk 4-point functions. So you have these 4 open string insertions on the boundary of the disk. You need to calculate the numbers first from the worldsheet perturbation theory, plug them into this integral and do this integral. So all that work, just which from the matrix integral side can be explained by this kind of dumb integral to get this number. So that's what we are doing right now with a great group of students at ICTS and my older collaborators. And there's one more open problem, which is higher order in G string. But let me just say that we want to fill in these dot, dot, dots. So this is the green gut pearl formula again. There are higher order terms, and we want to know what those are. Those are also completely fixed by S duality. But in the last 5 minutes, since it's a conference on basic science, let me give some personal remarks about some of the conversations I've had yesterday and even today about string theory. It's just one slide, so bear with me. So in popular media in recent years, string theory has started getting a very bad press. And many commentators have sounded ominous death knells, and this has started to, in fact, badly discourage young people to do research in string theory. And in fact, talking to colleagues, many departments around the world also don't want to hire string theorists. However, the state of the field is, and this is the physics content of this slide, we do not yet know what the basic degrees of freedom of string theory are. We only know it in certain limits, like either weak coupling or infinitely strong coupling or whatever, but we don't actually know what the fundamental degree of freedom is. What I mean by that, it was Einstein's insight that classical general relativity, the basic degree of freedom is the space-time metric. So forget about quantum string theory, just think about classical string theory. What is the analog degree of freedom there? We don't know, even today. We have all these dualities that work in different corners of moduli space, but it's fair to say that we do not even understand classical string theory at all. Okay, so the point is, even with this primitive state of affairs, string theory has produced new formulas, physics paradigms, and mathematical ideas that are beautiful and rich. And so, and we could learn a lot more if we did know of a fundamental formulation of string theory. So I think we need more research in string theory and not less. So that's it. Thanks for listening. Questions? Yeah.
Described by integrable systems such as KDB.
Yeah. Yeah.
So is it possible to use integrable system to compute this non-perturbative effects?
So yeah, so the string equation, what it can give you is so you can do a WKB type approximation in those string equations and the KDB hierarchies, but that will not fix some overall constants. It can tell you what the exponents are. So these action is e to the minus something. So you can get those from the string equation, but typically the WKB equation will have two solutions, and you'll have to fix the normalization constant again using some input in those. Like in the resurgence analyses, for example, they use that, but these prefactors need to be fixed using some other input. So what Marino, Schiappa, and other collaborators have done is studied the matrix integral carefully and this one eigenvalue instanton carefully and supplied those numbers.
Okay, thank you.
In this case, that's just the leading term. So if the quadratic term is 0, there could have been a cubic term, but we can show that all the cubic terms vanish in this case. So if you're just expanding in powers of the fields, the quadratic is 0, the cubic is 0, and so the next one is quartic. There would be higher order terms, x to the 5, x to the 6, but they will give higher powers of the coupling constant.
Yeah, anything to do with this, the moduli space interpretation of the array matrix integral,
The what, sorry?
the array function matrix integral.
Not directly, no.
Because you mentioned like this is like a perturbative chopping down the Riemann surface, but usually we use trivalent, right?
Trivalent. Yeah. This is like saying, this is not about chopping the moduli space, but about saying like you have a field theory on the D brane, and what are the terms in its action. So like typically, you know, when you have a field theory, the action starts with order x squared. That's the Gaussian. And then
That's
you
I
do.
understand, yes.
Yeah.
So I'm just trying to relate
Okay.
to this like known result of the KdV hierarchy of the arithmetic integral. Is there any?
To this particular one, I don't think there's at least I don't know of a direct connection between that. Yeah. Yes. Yes. Ah.
Thanks for the comment. Yeah, right.
Oh, okay. So you're asking whether all of these non-perturbative effects could be reproduced from the Kontsevich matrix
Exactly,
integral
yeah.
set.
Thanks for the comment. Yeah.
Oh, okay. Yeah, that is this cubic. But the cubic thing directly, if I'm not wrong, is dual to this 2, 1, right? Matrix integral, the quadratic one, which does not actually have these instanton effects. You can perturb it, but those perturbations, as far as I have seen the literature, are not completely explicitly written down. We say that there is this flow to these various models and they all live on the moduli space. But maybe working out the flow from the 2, 1 to the 2, 3 explicitly would be nice, because the 2, 3 has a single instanton. So if you can start with that Kontsevich matrix integral and do the appropriate deformation to go to this 2, 3 model and then compute the instantons, that would be interesting.
I see.
Yeah.
And thanks very much.
Yeah,
for the
okay,
comment.
okay.
Thank you.
It's not about expansion convention. It's a lot like more complicated examples. Like Newton perspective means like giant gravity contributions to a giant
Yes.
expansion. So one interesting question would be if you can give like string field, because that's very hard problem for that. No? That would imply potentials which are more complicated. No, it's
Yeah.
trigonometric.
Right.
So
right.
it's you have how to solve the inverse problem. It's
So what I guess what you're asking is, there are these unitary matrix integrals which have these double trace potentials, and they're known to have these giant graviton expansions. First of all, is there a string theory dual of those by themselves? Yeah. Yeah. Mm, Again, yeah, not that I know of directly. Yeah. I think it's an interesting question, regardless, to think of what this giant graviton expansion means in, let's say, type 2b string theory. But there could be like a smaller string theory that's just dual to this unitary matrix integral. But first one would have to discover that, I guess. Yeah. Okay, thank you.